Hey guys, it's Chill here. Welcome back to Hardware 3D. Today is the moment you've been waiting for. We're actually going to be working with the pipeline and rendering triangles today. And all of our hard work in 3D fundamentals is finally going to start to pay dividends. Because all that knowledge that we built up in those videos, that's going to become real important from this video onwards. All right, let's get this show started. We're going to create a function. We're going to call it draw test triangle. And we're going to put all our code that's required to draw the triangle. I'm going to jam it right in here. Put the definition right in the header file, just nice and sloppy. And this is the way I generally like to work when I'm first working with an API. I'm not going to waste a bunch of time building an amazing architecture because you know what? I don't even understand how the API is structured. How am I going to know what kind of architecture fits best? So don't even try. Just jam it all in there. Just do it all messy. Do your exploration, and when you've got your bearings, then you can think up a really nice organization and a structure that is going to scale. So we're putting everything in here, and the first thing we're going to do is, well, if we want to draw a triangle, we're probably going to have to be calling a function that draws stuff, right? Now, where do you think that function is going to be? Well, there's been some hints up until now. I've told you that the P device here, that one is used for when you're allocating shit. And the P context is used for configuring a pipeline and executing or issuing rendering commands. So you're probably going to choose P context, and then you go draw. And there you have it. You've got a draw function here. There's a bunch of them actually: draw, auto draw, index, draw. There's lots of them, but you'd probably want to just look at the one that just says draw to begin with. And here you get two parameters: the vertex count and the start vertex location. So you tell the amount of vertices to draw and basically the vertex to start with. So you probably want to be drawing 3 vertices, and you're going to want to start with the first one, which is 0, right? And there you go. We've issued our draw command. The only problem is, what vertices are we drawing? Because we didn't specify any vertices. So it's kind of weird if it just draws some random vertices. Obviously, there's got to be a way of feeding this some vertices. If you remember back to 3D fundamentals, the draw function, it took the geometry as a parameter and it drew that geometry. But it looks like Direct3D is a little different. It doesn't take geometry as a parameter, so you must have to set that with a different function. So here's a diagram of all the configurable parts of the Direct3D 11 pipeline. And a lot of this is going to be familiar to you guys from 3D fundamentals, because I kind of mimicked this architecture a little bit. So you're going to be familiar with the Vertex Shader. You're going to be familiar with the geometry shader, the idea of a rasterizer, a pixel shader. Output merger is basically just put pixel, right? And here we got the input assembler. That is kind of the same as the triangle assembler from the 3D fundamental pipeline, only it's before the Vertex Shader. And it's the input assembler that takes your vertices in, assembles triangles, and then sends those triangle vertices into the Vertex Shader to be manipulated. So obviously the input assembler is where we're going to have to bind our, that's where we're going to set our vertex input to. So now with your context, you type P context, an arrow, and you're going to see a whole bunch of different commands here. And they all start with things like HS, GS, DS. What does all this stuff mean? Well, those are just basically the initials of the pipeline stage from that diagram. So the input assembler commands start with IA, capital IA. And then you can just look through here. You can type set, and you'll see all the commands for setting stuff. And here we have set vertex buffers. And then we can look at these parameters, and we can see, you know, what things we've got to give this function in order to set a vertex buffer. So start slot, number of buffers. So we got to obviously give it a pointer. If you look at the name of the function, it gives us a hint. It says set index buffers, which tells us that we can set multiple buffers in a single function call. And that's why it takes the PP. It's a pointer to an array of pointers, which is a pointer to a pointer. And this is different than the other PP that you're used to. When you set a pointer to a single pointer, non-const, that's usually because it's an output parameter that allows the Direct3D function to set some variable outside of the function. But this PP is different because this PP is just a pointer to an array. pointer to an array of pointers. So it's important to make that distinction, and we'll see why in a little bit. But anyways, we've got some stuff here. Start slot, we don't know what that means. Strides, offsets, but we know what the name of the function is, right? We can look that stuff up. So if we read the documentation for the function, it tells us that the start slot, well, basically, you get one vertex buffer per slot. There's a maximum of 16 or 32 input slots. Now we're only binding a single vertex buffer, so we're just going to set this to 0, obviously. And then the number of vertex buffers is going to be 1. This is a lie. It says the type is a pointer, but it's actually a pointer to a pointer. But yeah, it's just the pointer to an array of vertex buffers. So we're going to have a pointer to an array that only has 1 entry. And then down here you have strides. So that is basically the distance between the first vertex and the second vertex, or the second vertex and the third vertex in bytes. And then pointer to an array of offset values. And that is where to start in each buffer in the array. Obviously, we're going to start at the beginning of ours. We're not going to do anything funky. So that is just going to be a 0. Now, one of the main takeaways of looking at this documentation is we're going to need some vertex buffers. And we see it's an ID3D11 type object. So it's a COM object representing some resource on the graphics card. And we're going to have to create that COM object. How do we do this? Well, you guys should already know this. We use pdevice to create stuff. Pdevice creates, pcontext issues commands. So pdevice, and we want to create buffer. That's it. It's not create vertex buffer or anything like that. There's one function, create buffer. It creates all the kinds of buffers that you want. And you're going to have to configure it, and you configure it with a descriptor, a buffer descriptor. And then there's sub-resource data. And then there is the PP, our familiar PP that we love to shower in. And that is what is going to be filled. So we need our buffer pointer to be filled. That much is pretty much clear. So I'm going to make my life easier. I'm going to do this namespace alias here. And then we're going to go WRL com putter. And we want an ID3D11 buffer. I believe that's the name of the thing we want. And we'll just call this one P vertex buffer. Beautiful. And now we want to call create buffer on that. But obviously, we don't just need the pointer to be filled. We also need a couple of descriptors. Well, we need this descriptor and a sub-resource data. So the descriptor, you know what these are already. They just configure what kind of buffer we want to create. So create this structure, D3D11 buffer desk. And well, let's take a look at what that all entails. So luckily there's not a lot in this structure here. We got the size of the structure in bytes. We got the usage, which is, what is this anyways? It says that the most typical value is default, but there's also immutable, dynamic, staging, and there's descriptions of them here. Default type is read and written to by the GPU only. Immutable is like a constant one. Once it's created, it cannot be written to by the GPU. And dynamic is accessible by both the GPU and the CPU. So if you're going to be updating that resource every frame, it's probably going to be dynamic. If it never changes, you might have some benefit in creating immutable, but the documentation says that this one is the normal one. So that's definitely the one we're going to be using. And then staging is for when the GPU creates some data and then it is returned back to the CPU. So this one we're probably not going to be using. We might use dynamic in the future. I might try immutable out, but we're going to probably stick to default for most things here. So there's the usage, and then your bind flags. How will it be bound to the pipeline? Now this is pretty important because this one tells you what kind of buffer it's going to be. It's going to be vertex, index, constant, shader, blah, 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 blah. Obviously, we want vertex buffer. So that's a no-brainer right there. CPU access, we're not going to allow the CPU to access this after it's been created, so that's going to be a big old 0. Then we've got miscellaneous flags for configuration. Oh, there's a whole bunch of them in here shared. We're not going to read through all this. For what we're doing, we don't need any of this bullshit. We might look at some of these in the future, but that's for the future. We don't need any special behavior, so we don't set any of these miscellaneous flags. And then the structure byte stride is the size of each element in the structure. That's basically the size of every vertex. So yeah, this descriptor describes the type of buffer we're creating, but there's nothing that tells this function what data to fill this buffer with, because we want to set it with some specific values for our vertices, right? So that's what this second parameter does. The sub-resource data is the actual data in some kind of array on the CPU side that will be transferred to the GPU and loaded into the newly created buffer. And this is a very small structure, only has 3 members. One is the pointer to the actual data, and then these two here, the pitch and the slice pitch, they only have to do with textures. They have nothing to do with any other types. Here it says, has no meaning for the other resource types. So all we gotta do is fill this guy with the pointer and we're all good to go. Now, in order to get that pointer, we need some data on our side. And in order to create some data, we need a structure to hold it. So let's create a struct, vertex. And our vertices are gonna be very simple. They're gonna be 2-dimensional vertices. So float X and float Y. That is all we need. And then to create our triangle, create an array of vertices like this, and we are going to fill them with vertex data. So if you visualize this yourself or you plot it out on paper, you will see that it's 3 vertices. The first one is the top of the triangle, the second vertex is the right corner, and the third is the bottom left corner. So that spells out 3 vertices of a triangle in clockwise winding, which I hope is the correct winding, but I guess we'll see. So now we have our CPU side data. Let's fill out our structures. And that's going to look something like this. They're set to all the values I told you. We set the byte width to the size of our array, and we set the byte stride to the size of a single vertex. Sub-resource data is very simple. We just set SD P system memory equal to vertices, right? And that will set this pointer into here. And now we're ready to create our mother truckin' buffer. So we pass the address of our descriptor, the address of the sub-resource structure, and we give it the PP that it so desires. Give us... Why is my IntelliSense? Sometimes it doesn't find shit and it makes me so mad. It makes me so mad. But anyways, this creates the buffer. So now we should have a buffer. Now, of course, this function returns H result, as you can see. So we should probably be doing error checking on this. So I'll wrap this call in our macro here, but it says, all right, because our macros are in the CPP file. We didn't put them in the header file so they wouldn't pollute all the other source files. So that's simple. All we got to do, move that bad boy and get rid of this because Visual Studio is retarded. And there we go. It should be, well, it turned purple, which is a good sign, but it is missing. Remember, it has a dependency. It needs H result in the scope here. Don't screw up my ordering there. Good. So H result, HR. There we go. Now it has an HR and now it is happy. And now we are creating our buffer and that should fill this vertex buffer with the goodness, the gooey goodness. Now we've got to set that to our pipeline. So we're going to call set vertex buffers. Start slot shall be 0. The number of buffers shall be 1. And now we need a pointer to the pointer to vertex buffers. So we can, well, to get a pointer to a pointer, we just take the pointer of P vertex buffer. And that'll give us a pointer to, it'll look like an array of a single vertex buffer. This should work, right? Anyways, P strides. So this function wants an array of strides and an array of offsets to match the array of vertex buffers. Since we only have one stride and one offset, what we can do is we can just create some simple integers, and then we can just pass pointers to them in here. So pointer to stride and pointer to offset. And there you go. That'll look like an array of a single element of each of these. What is your problem? Expected an expression. There we go. So I just added a couple of comments in here to make things easier for people to read afterwards, understand what's going on here. But yeah, all we do is we create these 3 vertices, create the buffer, bind it to the pipeline, draw that. What could go wrong? All we got to do now is go into app.cpp and call our draw test triangle. After we clear and before we end frame, everything should be perfect, right? Nothing could possibly go wrong. All right, well, my graphics have froze. My screen went blank. Oh, here we go. I'm back. It says device removed, error device hung. So device hung due to badly forwarded commands. Basically, our driver crashed. So we managed to crash the driver for our graphics card. That's probably not a good thing, right? So maybe we still need a little bit more to do, but that tells us that we crashed the driver. It doesn't tell us why the driver crashed, right? And that's a bit of a problem. You notice that these p context calls, none of them return anything. They return void. That's the way contexts work. So how do we get feedback? We can't wrap this function call in a throw info and get error information about it. But we're in debug, so we created our device on the debug layer. If we look at our output, we can see, oh, well, our debug output was telling us many things the whole god dang time. We just didn't realize it. So what you can do is when things are not working like you would think they are working, check that output. But you know Chili, right? He wants it all in his sexy little pop-up window that he can get right away. What if only one object is messing up, but it's in a whole big scene and you don't even notice it? I want that stuff to be brought to my notice post-haste. So what I'm going to do is I'm going to create another exception type. And this one is going to be info only. So because these guys, they don't return an H result, I can't use my normal exception with the H result. What I'm going to do is I'm going to create a macro that wraps a function call. This one here, the draw function call. It checks before the function call to see if there are any messages or to mark the current position in the output messages. Then you call the function call, and then it will check to see if there are any new messages that happened after the function call. And if there are any new debug messages, it'll throw an exception automatically. So I'm not going to bore you guys to tears with the details about this, but quick overview, I create a new type of exception called the info exception in graphics. And this one only stores info. It doesn't store the H result. And then in graphics.cpp, I create a macro here called info only. It calls infomanager.set. Then it calls the function call that is a parameter to the macro. And then after the function is called, it calls get messages, checks to see if that's empty. And if it's not empty, it throws an info exception with that information. Pretty simple, right? Down here is all the stuff for that info exception. It's pretty much the same as for the H result one, except it only has info, no H result BS in there. And then in here, we just wrap this draw call in graphics throw info only. Now I'm just going to cut to the chase here. None of these other p context calls, they don't really generate any debug information. All that debug information gets generated at once when you actually issue the draw command. So this is the only one we really need to wrap with our graphics throw info only macro. And now if we run this, instead of crashing our graphics driver, it immediately throws an exception and tells us a bunch of problems that we have. And these are going to be our clues as to what we have to do next in order to further our development of our pipeline. So we're going to follow these clues down one by one until we get no more errors. So the first one here is one that you guys should probably have already been able to predict from 3D fundamentals. A vertex shader is always required when drawn, but none is currently bound. So obviously, we have to set a vertex shader. You can't run a drawing pipeline without a vertex shader. You actually need vertex and pixel. I've mentioned that in 3D fundamentals. But let's do this one at a time. So we're going to have to create a vertex shader and bind it to the pipeline. Now, shaders are written in a language called HLSL, which stands for High Level Shader Language. So we're going to have to learn that programming language. The good news is that it is quite similar to C++. So it should not have a great cognitive load, but it's going to take a while. And I can't teach you everything about HLSL in a single video. I'm not going to. What I will do is I'll create a couple of simple shaders for our current task, and I will talk you through the process. So we need to add, it's got it right in here, HLSL. Actually, I don't know why it doesn't have pixel shader or vertex shader in here. That kind of scares me. So we're not going to choose any of these because I don't know what they're going to give us. We'll just choose text because I don't trust anything. I don't trust you. We're going to call it Vertex Shader.HLSL. Add it. There we go. So it added our Vertex Shader.HLSL. Just for organization here. It doesn't change the structure of anything. So, shader. What is it? It's basically just a function. It's a single function. It's a pure function. It takes an input. It gives an output. You know this from, 3D fundamentals, so I'm not going to beat a dead horse here. But what is the syntax? What is the output? Well, we need to output a position. That is the minimum that a vertex shader needs to give outputted. The position of the vertex so that it can be rasterized on the screen. Position has to be a 4-dimensional vector because of homogeneous coordinates. Again, that is from 3D fundamentals. Check out my video on homogeneous coordinates and the projective transform matrix. But anyways, so we got to return a 4-dimensional float. The name of the function, we should call it main because that's what it looks for by default. The compiler will look for an entry point called main for the vertex shader. Now, what is it going to take? Well, we have defined that our vertices for our triangles are 2-dimensional. So it's going to take a float 2, and we can call that position. All right. Now, inputs and outputs for shaders, they have 3 parts. They have the data type, which is going to be a vector type, float 3, float 2, float 4, or something else sometimes, but usually just vectors. It's going to be in the name of the variable. And at the end, you have something called the semantic, which is what are you using this thing for? And we are going to use it for position. So we'll put a position semantic on this. And in general, semantic names aren't fixed. You give it whatever name you want. You can call it butt plugs if you like. There are some special ones. We'll get into that in a little second here. So here's our function. Takes a float 2, outputs a float 4. What is it going to do? Well, we're not doing any transformation on our vertices. We just want to expand it from 2 dimensions to 4 dimensions. So we're going to go return float 4, and we want the position dot x and the position dot y, and the z is just going to be 0. There is no z for us, and the w is going to be 1, right? Because we don't want to do a perspective divide. Again, if you don't understand why that has to be 1, you really need to watch my 3D Fundamentals series. But anyways, here is our very simple shader. It won't compile because I've put a purposeful bug in here. But let's try and compile. Now, when you build your project, if you have HLSL in here, Visual Studio will build that as a shader. Well, it should. We'll see. Error, main function, return value, missing semantics. So yeah, like I said, the inputs and the outputs for a shader have to be labeled with semantics generally. So we've labeled our input 1 here as position, but we haven't labeled the output. So where do we put it? You might think you put it here, but no, you don't do that. You put it here after the function. And we want to call this as a special one. It's expecting a special semantic. Like, watch, what if I call this one butt plugs? I was going to call it, okay, well, yeah, whatever, doesn't matter. Let's just get on with the show here. We run that and we say invalid output semantic butt plugs. So we can't use that semantic for output. It's expecting a special one. And the one it's expecting is SV for system value position. Because, yeah, it needs a position of each vertex in order to rasterize it. That's the minimum that it needs to be able to rasterize a triangle, the position of the vertex. So if we build this now, it builds no problem. Everyone is happy. Now the output of the shader is a .cso file. That is a bytecode file. And that is what we are going to load at runtime when we want to create a shader. And then we'll bind that to the pipeline. So how do we load this? Well, it's just a binary byte file. You could load it with whatever you want, with fstream if you like. But there are provided functions for loading this, and we're going to use them to start off with. We have to add an extra dependency, so we might not want to use them in the future, but for right now, it seems like the easiest path for me. So, pragma comment, lib, we're going to link to D3D compiler, and you can use this to actually compile shaders at runtime, but we don't want to do that. We just want to link to this for the shader loading function specifically. And so we're going to include the header for that library. Let's create our vertex shader. So first of all, we need a com pointer to a vertex shader object. That's what's going to be filled. We got to get that PP, right? Now the function to load the shader bytecode is D3D read file to blob. A blob is just a binary blob of data. It could be anything. And that is what this function uses to store the contents of whatever file it reads. A blob, as we can see here, is also a COM object type. So we're going to want to get that blobby boy. We'll make a blobby boy here, and then we want to load our file. So we pass it the name of our compiled shader object, and we pass it the pp to the blob. And now we're all good to go. Notice that D3D read file to blob takes a wide string, even though our application is configured for narrow strings. This guy doesn't care about your configuration. He only wants wide strings, as far as I can tell. So that's what we're going to give him. And the only problem is this will expect to load it from our working directory, but the output of the Vertex Shader right now, it's putting it into the same directory as our executable is output to. And that's going to be a problem when we try to run this. So what we're going to do is we can configure how our shader is compiled. So in general, what do we want to do? Output files. So we don't want to output to the out directory. We want to output to the project directory. So set that. We can see under here in general, in HLSL compiler, you can set all sorts of things. You can set the entry point name to something other than main. Optimizations, you can turn them on or off, all good stuff. Debugging options, whatever. We don't care about that right now, but we might care about some of that later. Shader model that you're targeting, all that good stuff. So we set the output directory to our working directory, our project directory, and that means that the shader object, we can now load it like this without having to specify a nasty path. And that'll make my life a little easier, won't it? Now this thing returns H results, so we should wrap it. I don't think read file to blob, I don't think it generates debug info, but I'll wrap it with a graphics throw info anyways. And then finally here we call pdevice create vertex shader. And this guy takes a bunch of parameters, some of them going off the screen here. Oh, there we go, it's on the screen now, beautiful. So obviously you've got a pointer to the byte code, just a void pointer to a bunch of bytes. And then we get that from pblob pointer to get buffer pointer, and we get buffer size. And the third one, class linkage, that's a pretty advanced topic, but it's optional, so we set it to null pointer because we're not using that. And then we give it the customary pp, the pp to be filled vertex shader, and that should fill our vertex shader. Beautiful. And we wrap that with this because it's also a function here that returns H result. Awesome. This is annoying me here. I don't want to hard code this as 3 vertices. We can call std size on this array, and that'll give us the number of elements in the array, which is the number of vertices we want to draw. So that's a little better. But anyways, yeah, now we've loaded this vertex shader. Now we should bind the vertex shader to the pipeline. And that's incredibly straightforward. We just call pcontext vs set shader, and we get a pointer to the vertex shader. And what is this stuff? Probably dumb bullshit that we don't need. Yeah, class instances. Again, that stuff has nothing to do with us right now. That's an advanced topic. It has to do with this thing here that we set the null pointer. We're not using class stuff, so we're not going to set any of these numbers in here. This would actually be a null pointer, so I'll just fix that right now. But now we've got our vertex shader hopefully bound to our pipeline, loaded and bound. So if we rebuild to make sure that we wanted that shader to be rebuilt again. Argument conversion from size t to unsigned int. Oh yeah, because this returns a size t, so we should probably just go uint there. And that will be good. Build that again. I don't like having warnings. They make me mad, even when I'm just trying shit out. I still don't like warnings. All right, let's run and see what kind of pop-up box we get. Invalid arg, parameter is correct. Error info, create vertex shader, encoded vertex shader size doesn't match specified size. What is that now? Well, this, my dudes, is a very little tricky error, because it seemed like our shader was being compiled as a vertex shader properly. But watch this now. We get that error. I go into here. I specifically set the shader type to vertex shader, apply, and then I run again. And now we don't get that error anymore. We don't get that H result error. We only get info error from when we call draw, which is expected because we haven't set up everything on the pipeline yet. So what do we got here? Draw. Current primitive topology value 0 is not valid. and draw, the Vertex Shader expects application provided input data. So we've eliminated the error or the information that tells us, hey dude, where's your Vertex Shader? Because we've bound one and it seems to be properly bound. Now, the API isn't complaining about it. But we still haven't set some required settings. And one thing you might be scratching your head about is, well, Chili, why isn't it complaining that there's no pixel shader? Because, I mean, don't you need a pixel shader to draw the pixels? And the answer is yes. But in Direct3D, you can use the pipeline without having to render pixels. So if you look at this diagram here, you can only process vertices and then output that to a buffer as a stream output. And don't do any rasterizing, only output to stream. So you can just use the shader as a processor for vertex data without doing any rasterization. So that is why it doesn't complain. But obviously for us, we want a pixel shader. So let's get on that shit. But that, my friends, is a story for another day. This video is running a little long, so I'm going to cut it off right here. Stay tuned for part 2, where we are going to complete our pipeline and render our first triangle. Until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button, helps a lot. And I will see you soon with some more Hardware 3D.